about clustering techniques. So I'll first try to introduce what is clustering, and then we will see like what is the basic fundamentals of clustering. And there are several clustering algorithms which can be divided broadly into three types: partitional, hierarchical, and density-based cluster. And then we will touch up a little bit about cluster validity and what characteristics of data, cluster, and algorithm shape our results. Okay, so what is clustering? So the definition of clustering is very simple. It's grouping together of data points that are similar in some way or another. So you need to find groups, natural groups of data points in a data. So and then this similar word here is important because the groups, the points belonging to each cluster should be similar. Means the intra-cluster distance should be very small and inter-cluster distance should be large. That is, distance between the points which are in the same cluster should be small and the points which are in different clusters should be at a larger distance. Okay, so before we come into technicalities of all, I will try to motivate a little bit about what are the applications. So it's an unsupervised learning technique. Unsupervised means you don't know, you don't have any training data or training labels. So that the example will show okay, which data should belong to which group is not available. So which is usually true for all these novel data sets that are being collected nowadays. Maybe in a smart city or in healthcare or in all the other areas in which now we have IoT and all. So all the sensors that we implement, they collect lots and lots of data. So, but not much is known about those data beforehand. So we can apply clustering to them and see what are the natural groups of the data. So it's a method of data exploration which looks for patterns or structures in the data that are of interest. So it can be helpful in understanding the data. Once you discover the cluster, you can try to give some meaning to them. Okay, what does all these data points represent? Or you can summarize your data so that you don't have to store all that data, and it makes much more sense to understand what that data is. Now, what is not cluster analysis? So cluster analysis is usually sometimes confused with these terms. So first is simple segmentation, which is you divide the data based on whatever some parameter values. So for example, let's say you have a class of students and you sort them alphabetically, and then by last name you group them together. Like students having last name starting with A to D are in one group. So those are groups, but those are not natural cluster. Or results of a query. So you have a database, you find points whose value or whose x-axis is between 0.25 and 0.75. It will return some point of to you, but they are not clusters. Or supervised classification, where class label information is available. So that comes in the category of classification machine learning task. But clustering is different from that because in clustering we do not have this class label information. Okay. So one of the potential application could be in the electricity consumption pattern in smart cities, because nowadays we have smart homes and smart offices where all these power outlets have a smart meter connected to them. So you can measure, okay, how much is the electricity consumption at different times, during daytime, nighttime, during different seasons, to find out, okay, what are the patterns in this data. And it is very valuable for electricity companies, for government, and for users also to manage their power bills. Another application could be traffic assignment. So it could be either network traffic, like in like this internet, or it could be the physical road traffic. So we have this could be helpful in route planning to solve urban traffic congestions, or complex process depending on traffic pattern. We can have mass data processing, dynamic data collection, and all. So for example, for let's say transportation domain, we have lots of people going from one place to another. We can group their trajectories to know, okay, what are the common pattern or so that if let's say a public transport need to be started, what should be its routes and what should be its frequency, so that we can know, okay, so that it can cater to maximum number of people. Another one could be this financial services, because now all these banks and all, they provide several financial services. So they tend to group their customer based on some characteristics like average income, expenditure, credit score, and all. So different services and experience to different class of customers can be provided. It can also be helpful in fraud detection, because if something lies outside the natural, outside the normal clusters, they could be anomalies. And it is helpful in categorizing new customers. All right, now we will come to the technicalities of clustering. So if you remember the first slide that is shown here, so the clustering is grouping together of data points that are similar in some way. So this word similar is something which is to be noted here. And the another one is distance. So there's a notion of similarity between 2 points and a distance between 2 points. Now this notion is can be ambiguous, right? Because it's like, what do you call as close and what do you call as far and what do you call as similar, what do you call as dissimilar, is depend on application. So for example, for this data here, how many clusters can you see? So for different applications you can see. So for one, if you look at these points from a large distance, you can say, okay, there are 2 primary clusters. One cluster is this, second is this. Now, but if you look closer at each cluster, they can be further divided into 4 clusters like this, or even 6 clusters like this, based on what is the distance between them. Okay, so how do we define similarity? So the goal of clustering is to group together points which are similar in some way. Okay. So how do we define similarity? So for that, there's no single answer. So it would depend on what do we want to emphasize in the data, or what do we want to find in the data, or what is more important for our application. So for example, let's say you have a deck of cards which has 52 cards in it. So if our application is more for, let's say, color detection kind of thing. So if we are more concerned about color of the card, then the similarity or distance between 2 cards should be based on the color. So then we can get 2 clusters in that data, black cards and red cards. But if our application is more concerned about the number or letter on the card, then there will be 13 clusters. So it would be A, 2, 3, 4, 5 till 10, J, Q, K. And if we are concerned about the suit of the card or the shape that is drawn on the card, then the distance function should be based on that. And in that case, we will have 4 clusters. So diamond, club, heart, and spade. So you can see for single data set, we can get different clusters based on how we define the distance measure or what is more important to us for these clusters. Usually, a dissimilarity or distance measure is used. So a function, which is essentially a function dxy between 2 data points x and y. It's called a distance measure if it satisfies following properties. So first is the distance should be a positive number. It cannot be negative. So then distance of each point from itself should be 0. So dxy equals 0 implies x equals y and vice versa. Now this distance function is commutative. dxy should be equal to dyx and it should follow triangle inequality. So these are the properties. So any function which satisfy these properties can be used as a distance measure. So there are 2 major classes of distance measures. One is Euclidean, which is based on the location of point in the Euclidean space. And the second one is non-Euclidean, which is based on the different properties of the point. So we'll go through them now. So Euclidean distance. So Euclidean distance is mostly, there are a few options available. One is L2 now, or what in simple term we called as a straight line distance between any two. So if you have any 2 point which is defined by their coordinates in whatever dimensional space they are, so you make a straight line connecting these 2 points and calculate the distance between them. So this is the most common notion of a distance. Another option is the L1 norm, which is sum of the differences in each dimension. So this is more like, let's say you have a plain area, or let's say a city kind of thing, in which there are different roads, and you want to go from one point to another. Now you cannot go directly because there might be buildings in between, so you have to follow the road. So here we consider road to be along the x and y axis only. So in this case, that's called as a L1 norm, which is a common example is Manhattan distance. So the distance, if you had to travel along coordinates only, so the distance between x and y in this case would be 4 plus 3, 7 for L1 norm, and L2 norm would be 5. So you can use any distance based on what your application constraints are and other things. Apart from that, there are also non-Euclidean distances which can be used. So Euclidean distances are applicable if your data point can be represented in n-dimensional space. But if that's not the case, so for example, let's say your data points are sets or a string or a time series, then you cannot represent them in n-dimensional feature vector space. So then we can define other non-Euclidean distances such as Jacquard distance for sets A and B. So which is essentially 1 minus number of points in A intersection B divided by number of points in A union B. Similarly, if you have two vectors A and B, you can find angle between them as their distance. Or if you have two strings, then you can find, okay, how many inserts and deletes I need to do to string A to convert it to string B. That would be the distance, which is called as the edit distance. So the purpose to show here is because clustering is a very generic process. You can apply to any kind of data as long as you could define a appropriate distance measure based on application and properties of the data. All right, so once you have this distance measure, there are different types of clustering algorithms that can be applied. So on a broad level, clustering algorithm can be divided into 4 categories, although there are some others which might not belong to any of these categories, but there are very few of them. Okay, so the first category is a hierarchical clustering. So what hierarchical clustering does is it generates a hierarchy of cluster. Hierarchy means you have, let's say, the entire data, right? So you can say, okay, it can be divided into 2 groups, 1 and 2. Now cluster 1 can be further divided into 2 more groups, and so on. So that's called as a hierarchy. The next one is a centroid or medioid based clustering. What these algorithm does is they represent the cluster by the points belonging to each cluster by its centroid or medioid. The next one is a distribution based algorithm which try to fit a distribution to the data, and they try to find the parameters of that distribution. Another one is a density-based clustering algorithm, which try to group together points which have similar density. So these are all the different types of clustering algorithm. In today's talk, we will talk about all of them except the distribution-based algorithms. Okay, now before we move to other algorithms, there's one more classification of these clustering algorithms. So that is called as hierarchical versus partition. So I talked about hierarchical algorithm, right? So hierarchical algorithm generate a hierarchy of clusters, right? So you have two, let's say that entire data can be divided into 2 groups, then first group can be divided into 2 groups, and so on. So however, in partitional, you just get the final partition. That is, each data point can belong to one and only one cluster label, right? So the distinction is based on whether the set of the cluster is nested or unnested, because in first case you have nested sets, right? So you have one group, then few groups within it, and so on. Whereas for partitional clustering, division of data object into non-overlapping subsets. So you have each point belonging to to only one of the clusters. and each data object is in exactly one subset, whereas in hierarchical you have a nested clusters organized as a hierarchical tree. Okay, so just to show, so for example, let's say you have these data sets, and if you want to do it in a partitional clustering, so for example here you say, okay, these are my two cluster, all these points belong to cluster 1 and all these points belong to cluster 2, or you can say, okay, there is only one cluster in this data and all the points belong to only this cluster. Whereas for hierarchical, we can say, okay, all this data belong to one cluster, but P1 is, and then P2, P3, P4 belong to our group together. Then within this cluster, P2 and P3 are more close to each other. Or we can say, okay, P1 and P2 form one group, P3, P4 form another group, and they together form the entire data set. So usually we use a structure called as dendrogram to represent these hierarchy, which is more like a tree. So you have P1 is attached to cluster P2, P3, P4. Then within this cluster, you have P4 separate and P2, P3 together. Things like this. So this is the difference between hierarchical clustering and partitional clustering. Okay, so what are the popular algorithms? So for partitional clustering, we have k-means is a very popular clustering algorithm, and there are several variants of it to make it better. Whereas for hierarchical, we have two types of clustering algorithm, agglomerative and divisive. So we will come to that after next section. So in this section, we talk about partitional clustering, which is k-means and its variants. Okay, so k-means algorithm is a partitional clustering algorithm, and the how many cluster you want to find in it, which is called as usually written as k. K is the number of clusters. So this k must be given to the algorithm. We need to tell the algorithm, okay, in this data find 7 cluster or find 25 clusters. So this k must be given to the algorithm, and each cluster is associated with a centroid. So for whatever cluster is found by the k-means algorithm, there is a center point to it, which represent each cluster, and each point is assigned to the cluster with the closest centroid. So the algorithm is very simple. So let's say you are given some data and you need to find k clusters. So what you do initially is you randomly select k point as initial centroid, right? So you select k point and say, okay, these are my initial centroid. Then what you do is do the assignment. That is, for each point in the data set, find which centroid is this point closest to, or which centroid is closest to it, and assign it to that cluster. Once you assign all the points to different cluster, then you update your centroid, because now you have different points belonging to cluster. Now you can update the centroid and keep on doing it until the algorithm converges and there is not much change to the membership or to the centroids. So for example, let's say you have this data set which consists of few points, and you were to find k equals 3 clusters using k-means algorithm. So the first step we do is we pick 3 initial cluster centroid at random. So we select these 3 points, K1, K2 and K3 as initial centroid, which are randomly chosen. They could be any points in this XY space. All right. Next we do is assign each instance of to the closest cluster. So we have these 3 centroids, K1, K2, K3, which are shown by 3 colors, green, red and blue. And all the points are shown by these squares. So the points are color coded so that they are closest to show which centroid are they closest to. So all these red squares are closest to K2, so they are assigned to this red cluster. All these green squares are closest to K1, so they are assigned to green cluster, and similarly for blue. So this is after first iteration. You assign all these points to these clusters, and then you update the cluster center, right? Once all these points are shown to belong to this cluster, you update your centroid. So K2 was here. Once you have all these points, you find the new centroid with there should be no or very small change in cluster membership. Right? But sometimes what happens is the cluster membership keep on fluctuating due to some issues. So we usually put a upper limit on number of iterations so that we do not run into an infinite loop. And these are the final clusters that have been obtained. So you have cluster K1, which is shown by green, cluster K2, which is shown by red, blue, and the centroid represent the clusters. And so, for example, if you get a new point and you want to find out, okay, which cluster does that belong to? So we calculate the distance of that new point from K1, K2, and K3 centroids and assign it to the closest cluster. Okay. Now what we did here in k-means was, the first step was initial centroid were randomly chosen. Now this is a like an important task, and if you do not if the algorithm does not chooses these clusters these initial centroid wisely, the algorithm may not converge or the clustering results are very bad. Also, if you choose different clusters, different initial centroids, then the cluster produced by them are very different from one another. Okay. So in this case, closeness is measured by Euclidean distance, cosine similarity or correlation. So because what we do is when we assign points to each cluster, we find its distance to the centroid and find the closest one. So k-mean converts for these common similarity measures. Now, most of the convergence happens in first few iterations, and after that, there are very few changes in this. Now, coming to time complexity. So, time complexity of the algorithm is NKLD. So, N is number of points, K is the number of clusters, because at each iteration, you need to find the distance of N points to K clusters. Cluster centers, and then L is the number of iterations, and D is the number of attributes or the dimension of the data. So this is the time complexity of the k-means algorithm. All right. Now, once you know, okay, I found these clusters. Now, how do I know whether these clusters are good or bad? So, evaluating k-mean clusters is important. So for that, most common measure we use is sum of squared error, SSE. So what we do for that is, for each point, the error is the distance to the nearest cluster center. So we find the distance of each point from its cluster centroid and take the average of that or sum of that. So, so let's say we find two set of cluster for a given data. So that may be generated by two different runs of the k-means algorithm. And so we prefer the one which has smallest error, because in that case the points are much closer to its centroid, which is what is the one of the objectives of the clustering. So one easy way to reduce SSE. So there's a hack in that, because let's say if you increase the number of cluster, then the SSE will reduce, because so let's say you have n points and you say, okay, I want to find n cluster. Then each point belong to its own cluster. In that case, SSE would be 0. So so this is like a check which you need to do so that the clusters are not too high. All right. Now coming to what are the drawbacks of the k-means algorithm. So limitations of the k-means. So k-means usually have a problem when the clusters are of different sizes. So let's say you have different, let's say 2 or 3 clusters, and they have different size. One cluster is very big, one is small, or the cluster have different densities. Then also k-means would not be able to find the clusters, or the data has non-globular shape. Globular shape means the shape is like a circle. So in 2D space they are circle, in 3D they are sphere, in 4D they are 4-dimensional hypersphere, and so on. So if your clusters are shaped like this, then k-means is very good, where all the points are kind of like equally distributed about the centroid. But if that is not the case, then k-mean might not work very well. Also, if the data has some outliers or anomalies, then k-means algorithm does not perform well, because those anomalies would be assigned to one of the cluster, but they are very far away from the centroid. So for example, let's say you have these original points here, this green, this blue squares, red circles, and green triangles. So this belong to this first case, when size of the clusters are different. So this is small one, this is very big, this again is small. So if you apply k-means to it, this is the type of cluster that you will get, which is not at all representative of these this original cluster structure. Now this is different density. So if your clusters are of different density, so for example, this red is circle cluster, the points are a bit far from each other. So this is a sparse cluster, whereas blue and green are very dense cluster, right? Now if you apply k-means to it, what it will do is it will partition this sparse cluster into two, and the two dense clusters are merged together. So you get green, blue, and red. So this kind of, so this is one of the issue with the k-means. Also, this is for non-globular shaped cluster. So if your clusters are here, you can see, because this is a 2-dimensional space, your clusters are shaped of crescent. They are not circles, right? So so when you apply k-mean to this data, this is the type of cluster you obtain, which these bottom points are grouped in one cluster and top points are grouped in one cluster. So this is another issue with k-means. So if you have non-globular shaped clusters, then k-means might not work very well. All right, so what are the possible solutions? So one is, excuse me. Okay, so one way is to use a large value of k to find several groups of clusters within it, and then merge together the cluster. But again, this would be like a manual thing to do. So for example, here we can find 10 clusters in this. So we get all these groups, and then all these center clusters need to be merged together. Or here we can find, if we increase the number of clusters, then we'll get these two separate and then several clusters within it, which need to be merged later. Similarly here, we can increase the number of clusters and we get different 5 clusters in this crescent and 5 in this, and then we need to merge them later. So this is one of the way, but not a very efficient one. Next, we come to the initialization part, because in k-means, if you initialize wrong, then the results would not be very good. So for example, the k-means final clusters are sensitive to the initial seed, because so for example, let's say you have this data set in which you have green points, red points, and blue points. So there are 3 clusters in total. And if you choose the initial seed differently, you can get different results. So for example, here, if you all your initial centroid are in this top cluster, please increase the mouse pointer size. Okay, I don't know how to do that. Okay, I guess this might be yeah. So if we put all the initial seeds here, yeah. Hello. Okay. So if we put all the initial seed within this cluster, this is the final clusters that we obtain. Right? So if these are there, this is okay. So this is producing appropriate result. But if our seeds are like this, then this is the final clustering we get. So which is not appropriate. So the choice of the initial seed is very important for the output clusters. Now, so what are the problem when we select initial points? So k-mean works the best if the initial seeds are inside or close to the k clusters, right? But first of all, we don't know what are the clusters. If we know, then what's the need of doing this? Also, if the k is large, then it becomes very difficult to do this manually. So what we do is, so if let's say we have k clusters and each having n points, then probability that each of the k cluster has 1 point each is this, which is very small. So sometimes the initial centroid readjust themselves in right way. So whatever initial centroid you choose, sometimes they adjust themselves to go into the correct cluster, but this is not always guaranteed. So for that, an algorithm has been proposed, which is called as k-mean plus, which was proposed in 2007. So it specifies a procedure to initiate the cluster center, and it is guaranteed to find a solution that has a time complexity of log k. The k is number of cluster. Okay, so what we do is in this, first we choose C1 first center, which is uniformly at random among the data. So the first center is randomly chosen. All right. Then for each data point, we compute the distance between x and the nearest center that has already been chosen. All right. And we choose CI, which is using a weighted probability distribution. So point X is chosen with probability proportional to dx square, right? So we initially choose 1 point and then find the distance of that point from all the points, right? And then we choose the one which is which is probability proportional to dx square, right? So we try to choose the point which is at a farther distance from that. So in this way, we try to find points which are like kind of evenly distributed among the data set so that they may converge to the natural clusters. So for example, let's say this is our initial data, so which has 4 clusters. So the first point is chosen here. Now we see the distance of all these points from this. Now this point are at a largest distance, right? So the probability of them getting chosen as the next centroid is very high. So this point, let's say, is chosen. Now once we have this, all these points will be very close to a star and all these points. So the probability of them being chosen as a new centroid is less, whereas these points does not have any star close to them. So their probability of being chosen as a seed is high. So next iteration we choose this, and in the next one we choose this. So this ensure that points we have at least one initial seed at which is very belong to or very close to the natural clusters. All right. So this is one of the way to ensure that your initial seeds are good. Now, common precaution that we need to take when using k-means. So one is pre-processing. Pre-processing means we need to normalize the data and eliminate outliers, because outlier can cause the centroid to deviate too much from the clusters. And then post-processing need to be done, in which we eliminate a small cluster that may represent outlier and split loose cluster. So if there are some cluster which have very high SSC, that means that either the points are very sparse or the k-means had kind of joined two clusters together. And then merge cluster that are close and have relatively low SSC. So this is kind of a post-processing need to be done to find out the appropriate clusters. Okay, so this was about partitional clustering using k-means and its variants. Now we come to hierarchical clustering. So hierarchical clustering produces a set of nested clusters organized as a tree. So it can be visualized as a dendrogram, which is this tree structure you can see here. So it's a tree like diagram that records the sequence of mergers or splits. So how we merge 2 points, that is being recorded in this. And advantage is that it does not require k as an input, because for k-means we need to tell the algorithm, okay, find 5 clusters or find 7 clusters. But here we don't need that. And instead we use this dendrogram to infer the cluster structure. So for example, here you can see like this this point 1 and 3. So this is the distance, all right, and these are the points. So 1 and 3 are at a smallest distance, they are combined together. So you can see here 1 and 3 are joined together, they belong to this first cluster. After that 2 and 5 are joined and they are called as, let's say, a second cluster. Now this cluster 2 and 5 is closest to point 4. So this is joined to this point 4 and produces us the cluster 3, which is shown here as this red number. So the black numbers are data point numbers and red numbers are cluster number. Now this cluster 3 and cluster 1 are close to each other. So they are combined to form this cluster 4. So which is shown by this line. So this 1 3 is cluster 1 and 2 5 4 is cluster 3. Similarly, now this total cluster 4 is closest to 0.6 and generate cluster 5, which is the entire data set. So this is what this dendrogram represents. Alright, so there are two types of hierarchical clustering algorithm. One is agglomerative. So what agglomerative means, they starts with each point as an individual cluster. So they consider that all the different points are their individual clusters, and then it merge them into different cluster based on the distance. So at each step it merge the closest pair of cluster until only one cluster are left. All right, so it's shown here. So let's say we have all these points. So agglomerative, it consider all these points to be individual clusters. So you have all these small circles which shows they all are different clusters. Now we merge the closest cluster. So these two are very close to each other. So we combine them into one cluster. These two are close to each other, so we combine them into one cluster. These two are close to each other, we combine them. And then we group together all these clusters together to generate these two clusters, and then these two are combined again to form this one entire cluster. So this is agglomerative hierarchical cluster. The second one is divisive algorithm. So it starts with one inclusive cluster, and at each step split a cluster until each cluster contains an individual point. So this is opposite of agglomerative. So it consider all the points as single cluster and then try to break them up. So for example, at first stage, consider all of them into single cluster and then divide them into two, then divide them further till we get single point clusters. All right. So let's see what are the algorithms. So agglomerative clustering algorithm, it's a most popular hierarchical clustering technique. So in the basic form, it computes the proximity matrix or distance matrix between all the pair of points. So and then it starts with each data point being a separate cluster. So each point is a different cluster. Then it merge to closest cluster. So you'd find which point, which cluster or which data points are close to each other, and then it merge them into a single cluster and then update the proximity matrix. So this keeps on doing it until only a single cluster remains. So there are the key operation here is computation of the proximity of two clusters, right? So if you have just 2 points, then you can find the distance between them easily, like a Euclidean distance and all. But let's say you have 2 clusters, then how do we find the distance between 2 clusters? So let's say cluster 1 has 2 points, cluster 2 has 3 points. So what is the distance between these 2 clusters? So several approaches have been proposed which define the distance between these clusters, and they form the basis for various algorithms. All right. So initialization, let's say, start with cluster or individual points and a proximity matrix. So initially we consider all the points as different clusters, and then we try to find the proximity matrix, which is the distance between them. Okay, so after a few merging steps, we have some cluster. Let's say we have these clusters C1, C2, C3, C4, C5, which consist of a few points. And now this is the updated proximity matrix, which is between these clusters. Okay, now let's say in this step, we want to merge two closest subclusters C2 and C5. So we want to merge C2 and C5 into a single cluster. Okay, so first is how to update the proximity matrix after merging two clusters, right? Because now we generate a new cluster C2 union C5. So what would be these distances of this C2 union C5 new cluster to these C1, C3, C4 clusters? So this give rise to various algorithms. So let's say you have these two clusters, right? So this cluster has 4 points, this has again 4 points. So how do we define similarity or distance between them? So there are some methods that have been proposed. So the popular one are min distance or max distance or group average or distance between centroid or objective function based, such as Watt's method. So what min does is it's called as a single linkage. Yeah, and what it does is given two cluster, it find the minimum distance between any 2 points, right? So this point is closest to this point, and this is the minimum distance between these two clusters. So this is called as a single linkage distance. Max, what it does is trying to find the maximum distance between any 2 points belonging to 2. So this point is at a maximum distance from this point. So this would be the distance between these two clusters. Another one is the average distance. So it find all the pairwise distances and find the average of this. So that is called as the average linkage. And another one is it find the distance between centroids. So you find centroid of each cluster and find distance between that. So these different methods give rise to different clustering results. So for example, minimum or single linkage, the proximity of two clusters is based on two closest point in different cluster, right? So for example, here point 3 and 6 are closest, so you generate first cluster 1. Then 5 and 2 are closest, so you generate cluster 2. Now these 2 points has a minimum linkage distances between these 2 points, right? So they are merged together to form cluster 3. And this generate this dendrogram. Now, what are the advantage and disadvantage of single linkage? So advantage is it can handle non-elliptical shapes. So that is an advantage over k-means, because k-means could not generate good result if you have a non-globular cluster. But so for example, if you have a data set like this, then single linkage produces these clusters. Disadvantage, it is sensitive to noise and outliers, right? So if there are some noise points, that it generate bad results. So for example, if you have this type of data, so if you find 2 cluster, it find like this. But if you find 3 cluster, this 1 point is declared as a different cluster because it's a bit far away from the 2. So this is the noise point. So if you have a noise point, then single linkage does not generate good results. Now this was for single linkage, but if you use maximum or complete linkage, then proximity of two clusters based on the two most distance point, right? So here, let's say 2 and 5 are merged and 3 and 6 are merged. But earlier in single linkage, we could merge these two clusters because point 2 and point 3 were close to each other. But now we are finding maximum linkage. So the distance between these two clusters would be the distance between 0.5 and 6. So this one is long. So these two are not merged. Instead, 3 and 6 is merged with 0.4 and 5 and 2 is merged with 0.1. So we get a different clustering hierarchy if we use different linkage distance. So what are the advantage, disadvantage of complete linkage? So advantage is it is less susceptible to noise. So if we use complete linkage on this data set, we get these two clusters, which are okay. But disadvantage is it tend to break large clusters and it biased toward globular cluster, right? So it try to, it is similar to like k-means in this sense that it try to find circular clusters. So if your points are like this, it will generate these clustering results, which are not appropriate. Group average. So in this case, what we do is proximity of two clusters is the average of the pairwise proximity between the points in the two cluster, right? So we find the pairwise distance between all the points within the two cluster and then find the average of it. So advantage, it is less susceptible to noise and outliers, so which is a good thing. But again, it try to find globular cluster or circular clusters. Another choice we can use for linkage distance is the Ward similarity. So similarity of two clusters based on the increase in squared error when two clusters are merged. So it's in this what we do is we find the clusters and then we define the similarity, which is based on the how much squared error is increasing if we merge these two. So it is similar to group average if distance between point is distance is squared. But again, it is less susceptible to noise and outliers, biased toward globular cluster, and it's more like a hierarchical version of k-means, because here again we are trying to minimize the SSE squared error, which is the objective of the k-means algorithm. All right, so these are the for the same data, if we apply different clustering, different linkage distances, we get these different results. So for example, the minimum linkage, maximum linkage, group average, and Ward's method. So same data, same type of hierarchical clustering, but different linkage distance. generate different results. All right. So this was all agglomerative hierarchical clustering. The next one is divisive hierarchical clustering, which is generated using MST, minimum spanning tree. So what we do is we build the minimum spanning tree. So we start with one point, and in successive step we look for the closest pair of points such that one point in the current tree is not so let's say we start with 0.5, right? So if of the remaining points we find which is the closest to 0.5. So let's say 2 is closest. So we add this edge. Now we have 5 and 2 in the tree. Now 5 and 2 are there. Now we find of the remaining points which one is closest to any of these. So let's say 3 is closest. So we add this edge. Now we have 5, 2 and 3. Now in 5, 2 and 3 which one is closest? So let's say 4 is closest. So we add this edge. Then 6 is closest. So we add this edge, and then 1 is closest. So we add this edge. So in this way we build the minimum spanning tree. And based on this, once we have this, we can cut the longest edges to get the clusters. So this is what divisive is, because it generates one full cluster of all these states, and then we want to cut the longest edges one by one to generate smaller and smaller clusters. Now coming to the limitations of hierarchical clustering algorithms. So one is the time and space requirements are high because they are very computationally expensive. So because for if you have a data set which has n data points, so you need order n square space to store the proximity matrix and order n cube time complexity, which is very high. So they are not very appropriate for data set which has large number of points. And also once a decision is made to combine two cluster, it cannot be undone because your proximity matrix is updated, and again if you want to do it you have to start from zero. There is no global objective function which is directly minimized except for Ward clustering. And so again, based on what linkage distance you choose, it can be sensitive to noise or outlier. It can have difficulty handling clusters of different size and non-globular shape, and it can break large clusters. All right. So this was about hierarchical clustering. Now we come to density-based clustering algorithms. So in density-based clustering algorithm, the basic assumption is that clusters are dense regions in the data space, which was separated by regions of lower object density. So the clusters are dense regions. So where points are close to each other, those are clusters. And if there are no points or very few points between them, then they are usually outliers and are not considered part of cluster. So a cluster is defined as the maximal set of density connected points, right? So here the main concept here is the density connectivity, right? So any 2 points, they should be connected by density, means there should be some points between them. And it discovers clusters of arbitrary shape. So a few popular algorithms for density based clustering are DBSCAN and OptiX. So density definition. So the first thing we define here is an epsilon neighborhood. So for each data point, we draw a circle or a sphere of radius epsilon about it. Right? So objects within a radius of epsilon from an object, they are called as epsilon neighborhood. So so any point which is within this circle or sphere is a neighbor of this point. And then we call it as a high density point if this neighborhood contain at least some number of objects, which is again, so this should be min points, MINPPS. So min point means in this circle of radius epsilon about a point, there should be at least min points object. So these two are the parameters that need to be provided for the density clustering algorithm such as DBSCAN, and it try to find points which are connected in density. So here point P, this point When we draw a epsilon radius circle, there are 4 points within this circle. So its density is high because it has a 4 points within it. Whereas point Q, if you draw a epsilon neighborhood of Q, there are only 3 points within it. So its density is low. Also, there is a concept of core, border, and outlier points. So, given epsilon and min points, which are the parameters, we categorize the objects into 3 exclusive groups. Means points, data point belong to only one of these groups. So, one is a core point. So, a point P having more than min points within its epsilon neighborhood. So, if a point P has large number of points within its neighborhood, they are called as core points. Border points, a point which has fewer than min points, so it has less neighbors within its neighborhood, but it is reachable from a core point. It is connected to a core point, that is called as a border point. And a noise point is a point which is not a core point or a border. So for example, here you can see as the name suggests, core and border points. So core points are the points which are well inside a cluster. So for example, here, if you draw epsilon neighborhood, you have 1, 2, 3, 4, 5 points within it. So this is a core point. But the point which is on the boundary, like this, has fewer points, but it is connected to one of the core points. So this is the definition of core and border points, and an outlier which does not have enough points within its epsilon neighborhood and is not connected to any of the core points. So for this data set, which consists of different shapes, and there are lots of noise point also. So if we apply this core, border, and outlier points here, we can see all the points within the clusters are green one, which is like the core points. The blue one are the boundary ones, and outliers, the noise points, are declared as outliers here. All right, so once you have this, we define another concept called as density reachability. So directly density reachable. So an object Q is directly density reachable from P if P is a core object and Q is in P's neighborhood, right? So for example, let's say P is a core point and Q belong to its epsilon neighborhood, then Q is directly reachable from P because it is within its neighborhood. Now Q is so Q is directly density reachable from P, but P is not directly then. So this is not a inverse relationship because Q is not a core point. So density reachability is asymmetric. Now once you have one is directly density reachable, but another one is indirectly. So a point P is directly density reachable from P2. If P2 is directly density reachable from P1 and P1 is directly density reachable from Q. So if you could form a chain of points which are directly density reachable. So P is density reachable from P2, P2 is density reachable from P1, P1 is from Q. So we can say P is indirectly density reachable from Q. Now this form the basis of the DB-scan algorithm, which eliminate noise point and perform clustering on the remaining parts. So what it does is for each object O, if it is not classified, then it collect all the objects which are density reachable from O and assign them to a new cluster. If it is within density reachable from a point which is previously classified, it assign that point to that cluster, and so on. So for example, if we apply this DB-scan algorithm to this data set, which has lots of noise point, then all the original clusters are correctly identified by different colors, and the dark blue one shows noise point, which have been also find out easily. So advantages: linkage algorithm were not performing well, but the density-based algorithm do good with this. And it can handle cluster of different shapes and size. So here cluster shape and cluster size does not matter as long as they are density reachable. Okay. Now, when DBScan does not work well, so DBScan work well if the the clusters have similar density. So if your clusters have different densities, then it does not work well. Which is more likely to be a case when you have a high dimensional data. So let's say you have these points because what happens is in this DBScan there's a min points parameter, right? So if min point is set to very high, that means only very dense clusters are identified. If it is set to low, then all the noise point would also be identified. So that's the issue. So for example, here we have points in which we have very dense regions here and sparse regions here. So if we use min points as 4 and epsilon is 9.75, then we get this clustering result, which merge all these dense and these clusters together. But if we increase epsilon value, then these dense clusters are identified separately, but all others are declared as noise point, right? So this is because of this parameter setting. We get different results for different values of epsilon. Also, it is very sensitive to the parameter. So if we apply, so for example, here we have min points is 4 and epsilon is 0.5 here and 0.4 here. So once we goes from 0.5 to 0.4, this big cluster is partitioned into lots of small clusters, which is choosing the appropriate parameter in DBScan is a challenging task. Similarly here we have epsilon value 5, 3.5 and 3. So no value of epsilon is able to correctly identify the two clusters here. Here it merged all, here it partitioned them wrongly, and here there are lots and lots of clusters. Okay. To overcome these disadvantages, another algorithm was proposed. It's called as optics. So it was proposed to overcome following limitation of DBScan. So first is difficulty in choosing optimal value of a parameter, especially epsilon, because DBScan results are very, very sensitive to epsilon. So it works for data set which has clusters having varying density. So what it does is it introduced the concept of a nested density based cluster. So somewhat similar to hierarchical clustering, but based on density. So for a constant value of min points, clusters of lower value of epsilon are completely contained in those containing for a higher value of epsilon. So it kind of generate a nested summary of clusters based on their density. So what it does is it select an object which is density reachable with respect to the lowest value of epsilon, so that we are guaranteed that cluster with respect to higher density are finished first. Okay. So we started with the lowest value of epsilon, and then we extend DBScan for an infinite number of distance parameters, right, from 0 to epsilon. So first we find the value of epsilon, so that the highest density are finished, and then we keep on decreasing the value of epsilon. And it does not assign cluster membership as such, but outputs a cluster ordering which represent the density based clustering structure of the data. And objects in denser cluster are listed close to each other, which is equivalent to a density based clustering obtained from a wide range of parameter settings. So it kind of give you more like a hierarchy of points belonging to different clusters. So for example, in this data set, which we have 3 clusters, so for this, the output of the optics algorithm is what we call as a reachability plot. So it's a special kind of dendrogram. And so here the clusters are shown up as a valleys. So here this blue one represent this point, red one represent this point, and green one represent these points. Right? So these valleys are represent clusters, and these points which are like peaks kind of represent the connecting point or noise point in between. So this blue, red, and green show these three clusters. Okay, so we studied a few types of clustering algorithms which generate some clusters. Now the question arises, how good or bad the clusters are, because whatever cluster we find, are they any good or not? Because what happens is, for supervised classification algorithm, we usually know the ground truth. So there are a variety of measures to evaluate how good the model is, like accuracy, precision, recall, and so on. But for the clustering analysis, the analogous question is how to evaluate the goodness of the clustering result, or whatever cluster you obtained, are they any good or not? So as we seen using the example earlier, like clusters are very, application specific, and they depend on how do you choose your what is the application, and also the clusters are in the eye of beholder. So some people can say see clusters where there are none. So then how do we want to evaluate them? So to avoid finding patterns in noise, because if you have any random data, if you give it to a clustering algorithm, it will give you some clusters. So you don't want to do that. Then you want to compare different clustering algorithm, which algorithm perform better on which type of data, or we compare two set of clusters, or compare two clusters. So to answer these questions, we define what we call as a cluster validity. So finding cluster where there are not. So every clustering algorithm would find cluster in any data, whether there are clusters or not. So for example, you generate some random points and then give it to any clustering algorithm. It is bound to find some clusters in them. But are these clusters good or not? That is something we want to find out. So different aspects of cluster validation. So first one is determining clustering tendency. That is, we want to find whether the cluster has whether the data has clusters or not before applying the clustering algorithm. So that problem is called as clustering tendency. Then comparing clustering result to externally known result, that is class labels, and evaluating how well the clustering result fit the data without reference to external information, because that is not always available. Also, we want to find the two set of cluster, whether which is better or not, and determining the correct number of cluster, because this is usually an input, and if we do not know that, we experiment with different values of k, and then we choose which one is the best. So for this, there are some external indices which measure the extent to which cluster label matches externally supplied class label. If this is available, then we can use something like entropy or purity, etc., which kind of match the cluster labels with ground truth labels. But if that is not available, we have to restore to internal indices, which measure the goodness of a clustering structure without any external information, like sum of squared error, SSE. Apart from that, there are some relative indices which compare two different clustering or clusters. So one way to do that is via correlation. So we find a proximity matrix, which is the proximity or similarity between I and j element. And then we have a cluster label matrix, which is generated by the clustering algorithm. And then we find the correlation between P and S to see. So if the correlation is high, that means point belonging to same cluster are close to each other, which means that the clustering scheme is good. So it is ideal for partitional algorithms such as k-means, because for those cases only we have a cluster label matrix S, which shows each point belonging to one and only one cluster. But it is not a good for density or contiguity based clusters. So for example, here, let's say we have these three well separated clusters, which are, so this is called as compact well separated. So points within each cluster are compact and they are separated from each other. So if we find the correlation of the similarity matrix and their labels, we get 0.92, which is a very high value, which represent that these clusters are good. But for this, correlation is 0.58, which is less, which means the points belonging to same cluster are not very close to each other, and they are close to other clusters. Another way is to using similarity matrix for cluster validation. So in this, what we do is we order the similarity value matrix with respect to cluster label and inspect visually. So this is a visual approach. So in this, we find the distance matrix and then reorder them based on the cluster labels. So all the point belonging to red cluster are here, point belonging to green cluster are here, and then blue cluster are here. So once we do that, then these dark blocks along the diagonal or here, the values are, the red represent high correlation similarity values. So this means all these points within this cluster are very similar to each other, but they are dissimilar to other clusters. So this represents a good cluster. Clusters in random data are not so crisp, and dark blocks along the diagonal are not clearly distinguishable. So this is for the random data that we did here. So for this random data, if we apply this dbScan, k-means, and complete linkage algorithm, we do get something here, but you see these dark blocks are not very high value as compared to this. So these are all very, very red, and these are all blue. But here, these red are not as dark, and there's some red here. So this represents that these clustering is not very good. Similarly, we can have, if the data has both cluster as well as noise, then these noise points are we can find the clusters and noise separately, because cluster are shown by these red blocks or having very high similarity values, and noise points are here which has low similarity values to each other. So this is one way to find clusters. Another is internal cluster validity measure, such as sum of squared error, SSE. So SSE is good for comparing two clustering or two clusters, and it can also be used to find the number of clusters. So for example, for this data set, when we apply k-means for different values of k, we get this SSE. So from this, we can choose the optimal value as the elbow value, because elbow value is, so because if we have very large value of k, then the SSE would be low, because if each point is assigned to its own cluster, SSE would be 0. But we do not want a very large value of k. We want to find this optimal value, which is given by this elbow. So one elbow can be found here, which is 5. So where each of these two are merged. So this is 1 cluster, 2 cluster, 3 cluster, 4 cluster, 5 cluster, or we can have a 10 where each of these cluster is separate. So we can have these two values of k. But if your data set is more complex and there are lots of noise, then this curve would be much more smooth, and finding an elbow would not be easy. So elbow is not clear, and noise point lead to loss of quality. Also, also there are other internal measures such as cohesion and separation. So cluster cohesion measures how closely related are objects in a cluster. So it could be within cluster SSE. So it find like how close the objects are within the cluster. So it find all these pairwise distances and find the average distance of each point from the centroid and the average of them. Another one is cluster separation, which find out how distance two clusters are. So it could be between cluster SSE. So it would be the average of all these points. Then we combine these idea of both cohesion and separation using one way to measure it is called as Silhouette coefficient. So for each point, we find A, which is the average distance of I to the points in its cluster, and B, which is the minimum of average distance of I to other clusters. So it's essentially the average distance of point I to the closest cluster. And the Silhouette coefficient is then defined as B minus A. So B would be the average from the nearest cluster, divide minus A would be the average distance from within cluster. So S range between 0 and 1. So if S is high value, close to 1 means we have well separated cluster, and close to 0 means the clusters are not good. Now, final comment on cluster validity. So the validation of clustering structure is the most difficult and frustrating part of cluster analysis, because You have a data, you can apply any clustering algorithm. But to decide whether the clusters are good or not is a challenging task. And if we do not spend time on this part, then our cluster analysis does not produce meaningful results in this. Okay, now the final comments. So characteristics of data, clusters, and clustering algorithms. So whenever you are planning to apply any clustering algorithm on any data, we need to take into consideration characteristics of all this. So once we know what all this is, decide whether to go for cluster analysis or not, which algorithm to use. Then we will be able to answer. I think this presentation today tried to answer these things, whether decide whether to go for cluster analysis or not. So if the data has cluster, then we should go for. And which algorithm to use depend on what type of clusters could there be. If they are globular, then we can go for k-means. If we want to find hierarchy, then we go for hierarchical clustering. If the density varies, then we should go for density-based algorithm. Then we can choose appropriate distance measure, number of clusters, other algorithm-specific parameter, find the results, and last but not the least, validate and interpret the results. We should be able to show, okay, these points are indeed belong to different clusters, and this is the physical significance behind it. So characteristics of data such as high dimensionality, size, sparsity, noise, type of attribute, type of data set, difference in attribute scales, so that we should scale, and then property of data space. Can you define meaningful centered? So for example, if it is in k dimensional space, then we can define centered. Otherwise, we can. Characteristics of clusters, data distribution. What are the shape of cluster? Different size. Are there different densities? Are the clusters separated well or not? Relationship between clusters. Type of clusters like centroid based, contiguity based, density based, subspace clusters. And there are various characteristics of clustering algorithms such as order dependence, like the way in which it processes the data. Non-deterministic. Can you get, is it deterministic or probabilistic? Parameter selection, which parameter to use? Is it scalable? Like if you have large data, would it work? What is the model? How does it cluster the data? And what optimization technique is it used?